Hi, my name is David Ryan. Today we will be doing a sample presentation for Pluralsight. It will be physics modeling in Microsoft Visual Studio using C# language. Let us go over some prerequisites and the outline for this lesson. Prerequisites include a basic understanding of physics, that is to say, late high school or early college. Basic coding knowledge assumes that the student knows how to make a for loop and to initialize a few constant variables. The outline will go as follows: model development, program sketch, and then we will develop the program in C#. Let us take a look at the physical model. Here we have the spring mass damper system. X denotes the coordinate system. The square with the M in the center is the mass. The resistor-looking symbol with the K next to it is the spring and its spring constant. To the left of this is the damper, denoted by the Greek symbol. Let us take a look at the free body diagram. We have two forces acting on the mass if the mass is accelerating upward. These forces are the force of the dampener, denoted by Fd, and the force of the spring, denoted by Fs. On the right-hand side of these equations represent the state laws associated with the dampener and the spring. In this case, the velocity of the mass state is x dot, and the position is x. We apply Newton's second law to this model, and we obtain on the bottom, after balancing the equation, a second-order differential equation. After we have this second-order differential equation, it is convenient to turn this into state space form. This allows first-order differential equations to be extracted from a second-order differential equation. Let us let x1 equal x, take two derivatives, and substitute these new state variables into the second-order differential equation from the last one. By doing this, we obtain a system of two first-order differential equations that we can put into matrix form. We can denote the derivatives on the left-hand side as x hat, and on the right-hand side we have A, which is the dynamics matrix multiplied by the state matrix X. We will be using the Ford-Euler algorithm in order to integrate these equations in time. Let us go ahead and discretize the previous second-order differential equation. We now have this discrete equation. The current state is equal to the previous state plus the dynamics matrix multiplied by the previous state times the discretization in time. This discretization can theoretically go for all time from the initial time to time infinity. We can conveniently rewrite this as the product between the previous state times these combined matrices, I denoted as the identity matrix, equaling to the next state. With the prerequisites out of the way, let us go ahead and start coding in MATLAB. First, we're going to type edit into the terminal window. Press enter. Here we have the editor in MATLAB. So let's go ahead and start with some variables. Let's define the three parameters. The spring constant, we'll call it K. We'll let everything equal 1 here. Next, we'll look at the damping factor. Call this D. Set this equal to 1. Next, we'll go ahead and set the mass.
Now we're going to go ahead and set the dynamics matrix that we have from the derivation. Let us now set the initial condition. This is otherwise known as the state of the system. The first row is position, the second row is velocity. Let us go ahead and implement the forward Euler algorithm. We'll start with a for loop between 1 and 10. Sorry, 1 to 100. Let us have the time step be 1/100th of a second. So the idea is that we'll run this state between 0 to 1 second. Within the for loop, we're setting the forward Euler method. So we're going to go ahead and save every state for every time. This will allow us to plot displacement and velocity as a function of time at the end of the for loop. It is important to note that MATLAB is case sensitive. As you'll see with some of the errors that we have later, Xsave and Tsave do not have the same capitalization. As a result, this particular program will not run. In the next few minutes, you'll see these corrections. We're also going to keep track of the time variable t. Let's go ahead and use the plot function. We're going to plot the first row of Xsave as well as the first row of Tsave. This will plot displacement as a function of time. In this particular case, it'll run between 0 and 1 second. As I said earlier, we'll try to run this, but we'll notice several capitalization mistakes in the variables. Let us go ahead and save it as a spring mass damper system. Later, we'll abbreviate it to spring mass damping system. Let us go ahead and make the capitalization corrections. It should also be important to note that when we run this program, you'll notice that the variables are not suppressed with a semicolon. As a result, you'll see the answers as they run in the for loop in the terminal window. This will slow down the computation, so we will suppress it with a semicolon, as you'll see here. Let us also go ahead and increase the time to 10 seconds. This will give us the characteristic response of a spring mass damper system, as you see in the plot here. Let us add some labels to the graph. The x dimension will be time, the y dimension will be displacement. As you can see, MATLAB can be a great tool for mapping the dynamic response of physical systems. Thank you for your time today, and I hope Pluralsight is satisfied with the results. Thank you so much.